Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we explained Carnot cycle. As you know, it consisted of two adiabatic processes and two isothermal processes. Today my topic is first the absolute temperature scale. Absolute temperature scale is also called Kelvin scale. Now how this scale is defined. Remember, we have already discussed temperature scales. We have discussed Celsius scale. We have discussed Fahrenheit scale. We have discussed ideal gas temperature scale, right? And you know, we at that time said that ideal gas temperature scale is defined uh, up to the temperature of about 2 degrees, at which helium is used as a gas in the thermometer. Below that, we don't have any substance which can exist as a gas inside the thermometer. So for those temperatures, we use absolute temperature scale, or it is also called Kelvin scale. And we also at that time said that ideal gas temperature scale and Kelvin or absolute temperature scale coincide at temperatures where both scales are defined, that is about 2 degree. So we uh, have the same symbol for ideal gas temperature scale and Kelvin scale, or absolute temperature scale, that is capital T. Now today we are going to understand how this absolute temperature scale is defined. We said that when we discuss Carnot theorem, I repeat that Carnot theorem is saying that no engine working between two given heat reservoirs can be more efficient than a reversible engine working between those reservoirs. And what was the corollary of that? Corollary was all reversible engines working between the same two reservoirs have the same efficiency. I repeat, all reversible engines working working between the same two reservoirs have the same efficiency, right? This is a corollary to Carnot theorem. That means if I have two reservoirs, this is my use another color. This is my hot reservoir at temperature TH, and this is my cold reservoir at temperature Tc. Now, if I use any reversible engine between these, any reversible engine I operate between these two reservoirs, any reversible engine, it will have the same efficiency which we have already denoted by epsilon, right? And we know efficiency of heat engine. We've already done that. Efficiency of a heat engine is written as 1 minus QC by QH. What is QC? Amount of heat rejected by the engine in one cycle, the cold reservoir, and QH is amount of heat absorbed by the engine per cycle from the hot reservoir. Now we keep this QC in modulus because our convention is that heat rejected is taken as negative, heat absorbed is taken as positive, but we are only taking the modulus of the heat rejected, absolute value, right? Now, since efficiency of all reversible engines working between two given reservoirs is same no matter what kind of system is used for the heat engine. This is important. You use any system, any working substance for your reversible engine, but for a given pair of heat reservoirs, it will have the same efficiency. So as long as the engine performs in a reversible cycle, what is the meaning of that? In reversible cycle, we absorb or reject heat isothermally. So in reversible cycle, heat absorption and rejection takes place isothermally and quasi-statically. And system changes its temperature adiabatically and quasi-statically. Remember Carnot cycle in which we have two isothermal processes. One is isothermal expansion and second is isothermal compression. You know heat absorption takes place in isothermal expansion and heat rejection takes place in isothermal compression, and the temperature of the system changes during adiabatic processes. In adiabatic expansion, temperature decreases, and in adiabatic compression, temperature of the system increases, right? So when reversible engine is operating between two given pair of reservoirs, whatever the system used in the engine, efficiency is going to be same. Now there is only one characteristic of a heat reservoir which specifies it as a reservoir, that is its temperature, right? So the efficiency of a Carnot engine, which is reversible engine, must depend on the temperatures of the two reservoirs, right? I repeat, I said any reversible engine or Carnot engine, Carnot is a reversible engine, operating between two given reservoirs has the same efficiency, whatever the system is used in the engine. Now, there is only one characteristic of the reservoirs which is important or which specifies them as a reservoir, that is their temperature. So conclusion is that the efficiency of a Carnot engine or reversible engine must depend only on the temperatures of the two reservoirs, because if we change the temperature of the pair of reservoirs, then automatically efficiency will change. But for a given pair of reservoirs, efficiency for all reversible engines or Carnot engines will be same. Therefore, I can write this equation as, let me move to next page. I can write QC by QH is equal to 1 minus ER. The same equation, I'm taking it to the left hand side and efficiency to the right hand side. This becomes positive, this becomes negative. But one change I have made, I have written the subscript R with a E, with epsilon. So here, now epsilon R is what? It is efficiency of a reversible engine. Like Carnot engine. So efficiency of a reversible engine depends only on the temperatures of the given reservoirs. That means this right hand side depends only on the temperatures of the two given reservoirs. Since the right hand side depends only on the temperatures of the reservoirs, that means for a given pair of reservoirs, this ratio is fixed and unique. So we define absolute temperature scale using this idea. How? So absolute temperature scale, absolute temperature scale is defined as Tc by Th is equal to mod Qc by Qh. This is the defining equation of absolute temperature scale. What is the meaning of that? Meaning of that is, if we have two bodies, hot and cold, they will become our hot reservoir and cold reservoir. This hot, this cold. Now, in order to find the ratio of their temperatures, Tc by Th, we have to operate a reversible or Carnot engine between these two bodies and carefully measure the heat rejected and heat absorbed, if any, right? And substitute those values of heat in this equation to get the ratio of their absolute temperatures. Got it? I'm saying if I have hot reservoir and cold reservoir, you can say hot body and a cold body, and you want to find the ratio. It is my hot reservoir, it is my cold reservoir. You want to find the ratio of their absolute temperatures or temperatures in Kelvin, Th by Tc or Tc by Th. We have to take a reversible engine and operate between these two reservoirs. This is my Carnot engine or reversible engine, and take a careful measurement of heat rejected and heat absorbed, Qc and Qh, in order to find the ratio of their temperatures, right? Now this equation gives us the ratio of the temperatures in on absolute temperature scale. If we want to find the temperature of a given substance, not the ratio of the temperatures of two systems, then we use triple point of water as our reference state. Triple point of water is used as the reference state, and its temperature is assigned as how much? To 73.16 degree Kelvin. To 73.16 degree Kelvin, or you write just Kelvin, to 73.16 kelvins. It is assigned to the triple point of water. Then if you want to specify the absolute temperature of some system, you take one system as triple point of water, assign this much temperature to that, then operate Carnot engine between that system and triple point of water, measure QC and QH, and specify the temperature or assign the temperature to that system. So this is how we define absolute temperature scale. So you can see now, since QC by QH is TC by TH, therefore efficiency of Carnot engine or reversible engine can be written as, or written in terms of, the absolute temperatures of the reservoirs. You can write it 1 minus Tc by Th. So efficiency of a Carnot engine or reversible engine is given by 1 minus Tc by Th, where Tc is the absolute temperature of cold reservoir and Th is the absolute temperature of hot reservoir. And you also know, as I have said it at the start of this lecture, that the ideal gas temperature scale and Kelvin scale coincide when both are defined, that is at and above 2 degree Kelvin, right? This was one thing. Let me move to next. We will do a sample problem now. The problem goes like this. The Carnot engine or Carnot cycle, not Carnot engine, the Carnot cycle shown in figure 1 is performed using an ideal gas. Using an ideal gas. Show that the ratio of the heat rejected to the heat absorbed equals the ratio of the ideal gas temperatures of the heat reservoirs. Let me make the figure. The figure already. This. So this is my PV diagram. Let this be my point 1, point 2, point 3, and point 4. This is first step, and there is second step. Sorry, let me make it clear. This is second step. So it is not accurate, but you can understand. And this is third step, and this is fourth step. This is my Carnot engine, Carnot cycle. This is figure 1. So 1 to 2, there is isothermal expansion taking place. 2 to 3, adiabatic expansion. 3 to 4, isothermal compression, and 4 to 1, adiabatic compression. Now I repeat the question. The question is saying the Carnot cycle shown in figure 1, which is shown, is performed using an ideal gas. That means working substance, we use our ideal gas as working substance. Now show that the ratio of the heat rejected to the heat absorbed. We have to show that the ratio of heat rejected, that's mod QC, to the heat absorbed, that is QH, equals the ratio of the ideal gas temperatures of the heat reservoirs, right? We have to show that QC by QH is TC by TH, where TC and TH are the ideal gas temperatures of the heat reservoirs. Now you know ideal gas temperatures are the same as absolute temperature scales. That is given that we are using ideal gas as our working substance. Well, let us proceed. Now the solution goes like this. We know the equation of state of an ideal gas is normally written as PV is equal to NR T. P is pressure, V is volume, N is number of moles, R is universal gas constant, capital T is absolute temperature scale. Now we deliberately write it PV is equal to NR small t, where T small t we take as the ideal gas temperature scale. Small t is ideal gas temperature of the gas, right? So we deliberately write small t in order to check that the ratio of heat rejected to heat absorbed is the ratio of ideal gas temperatures, right? Now what we have to show to prove or to show is QC by QH is equal to TC by TH. This is our aim to find or to prove, right? Now we first consider the first step is isothermal expansion. This is what? Isothermal expansion. From point 1 to point 2, isothermal expansion takes place. We know for an ideal gas, internal energy is function of only temperature Temperature of the gas stays constant during isothermal expansion. So internal energy doesn't change. Work is done by the gas because it is expanding against the piston or surroundings. So from first law, work done by the gas in this isothermal expansion equals the heat absorbed. Now first we find the work done. So work done, this is my work done, right? I use the symbol work done 1 to 2. Subscript I use 1 to 2. That means work done by the ideal gas as it moves from point 1 to point 2 is what? Integral 1 to 2 PdV. Now instead of P, I can write it be 1 to 2. Instead of P, I write NR TH by V dV. What is TH? Where TH is the ideal gas temperature of the hot reservoir. Ideal gas temperature of the hot reservoir. We have used it here in this equation. We have solved it for P as nRT by V. Now we have replaced it P by nRT by V, but I have used the subscript H in order to indicate that this expansion is taking place at the temperature of hot reservoir, right? So it will become NR NRTH, temperature is constant, then it will become ln natural log of V2 by V1. NRTH NRTH natural log of V2 by V1. So this is work done by the gas during first step. It is also equal to heat absorbed. So I can write it is equal to QH. It is also W1 to 2, right? This is heat absorbed by the ideal gas during isothermal expansion. Now similarly, heat rejected to the cold reservoir equals the work done on the gas in the isothermal compression. Now isothermal compression takes place from point 3 to point 4, this isothermal compression. Now the heat is rejected during this step, and heat rejected to the cold reservoir equals the work done on the gas. Here work is being done on the gas, right? And this work done takes place at the temperature of the cold reservoir Tc. This is isothermal compression. Work is done on the gas, and that work done on the gas equals the heat rejected by the gas to the cold reservoir. Now this work is of the same magnitude as that done by the gas if it expands from state 4 to state 3, right? I'm saying this work is of the same magnitude. Magnitude of the work is same as if the gas expands from state 4 to state 3. Therefore, I can write heat rejected as heat rejected can be written as NR Tc ln V3 by V4, because my final state is V state 3. I'm taking as if gas is expanded, because magnitude of the work will be same, that will be equal to heat rejected. My heat rejected is nRTC ln natural logarithm of V3 by V1, where V3 is the volume at state 3 or 0.3 in the diagram. V4 is the volume of the gas at state 4 or 0.4 in the diagram. Therefore, the ratio of these heats is QC by QH. Ratio of these heats is QC by QH is TC by TH. TC is the ideal gas temperature of the cold reservoir. Ln V3 by V4, here ln V2 by V1. QC by QH is TC by TH. Natural log of V3 by V4 divided by natural log of V2 by V1. Now we want to relate, next step is we want to relate V1, V2, V3 and V4, right? Now these volumes, if you see in the diagram, now volume 2 and 3 and 1 and 4. This is an adiabatic path. This adiabatic path. 1 and 4 are connected by also an adiabatic path. 2 and 3 are also connected by an adiabatic path. And we know for an adiabatic path, for an ideal gas, let me move to the next page. For an adiabatic path of an ideal gas, PV raised power gamma, where gamma is what? Remember, gamma is Cp by Cv, where Cp is heat capacity at constant pressure, Cv is heat capacity at constant volume. So PV raised by gamma is constant. And we can also use the ideal gas equation. So we can eliminate pressure. We can write, instead of P, I can write nR T by V raised per gamma is equal constant, right? PV raised per gamma is constant. P is replaced by nRT by V. So it's nRT by V raised per gamma, or I can write TV raised by gamma minus 1 is constant, because nR is also constant. Or I can write T V raised by gamma minus 1 is constant. So this is for ideal gas when it undergoes an adiabatic process. This nR I have absorbed in this constant. TV raised by gamma minus 1 is constant. Now applying this equation to states 2 and 3, because states 2 and 3 are connected by an adiabatic path. So applying, I name this equation, applying first to states 2 and 3, which are connected by an adiabatic path. So I can write T H V2 raised power gamma minus 1 is equal to Tc V3 raised power gamma minus 1. Th V2 raised power gamma minus 1 is equal to Tc V3 raised power gamma minus 1. Why so? Because at state 3, gas has temperature of cold reservoir, and state 2, it has temperature of hot reservoir. That's why this. Similarly, for states 4 and 1, similarly for states 4 and 1, which are also connected by an adiabatic path, that's adiabatic compression, I can write Th V1 raised power gamma minus 1 is equal to Tc V4 raised power gamma minus 1. Because at 1, temperature is as that of the hot reservoir, that's why this Th, and at state 4, it has the gas has temperature of the cold reservoir. Now if we divide these two equations, that is, let me name this second and third. Dividing second by third gives, dividing equation second by third gives what? It gives us V2 by V1 raised power gamma minus 1 is equal to V3 by V4 raised power gamma minus 1. Is when we divide these two equations, Th and Th cancels out on left hand side, Tc on right hand side. So we get this, right? So V2 by V1 is equal to V3 by V4 implies V2 by V1 is equal to V3 by V4, and natural log of V2 by V1 is equal to natural log of V3 by V4. Right? So therefore, we can cancel the logarithmic terms in our previous equation. Let us move to this equation. Let me name this equation A. We have proved that natural log of V3 by V4 is equal to natural log of V2 by V1. So these two terms can cancel out. So I can write using an A. Let me name this 4. So using 4 in equation A, using 4 in equation A, we get QC by QH is equal to TC by TH. This was my A, this was my 4, this was my A, is cancelled out, so I get this. So I have proved my result. I have showed that the ratio of, this is my proof. We have showed that the ratio of the ideal gas temperatures of the two reservoirs is the same as the ratio of the ratio of uh, heats rejected and absorbed, and we know the ideal gas temperature scale and absolute temperature scale is same. You can write it as Tc by Th also. So this is all for today. Thank you. Be sincere with your studies and don't forget to subscribe my channel. God bless you. Assalamu alaikum.